Okay, so in this lesson we are going to solve quadratic equations by factoring. And so this first page is a factoring review, and each of these sections is a different case for factoring. And so this first section, we're going to talk about how to factor out a GCF. And so a GCF is a factor, the greatest common factor, that divides each term. And so looking at our first quadratic, these two terms can both be divided by 2, and then they can also both be divided by x. Okay, and so we would put the 2x here, and then inside the parentheses, we would put the result of dividing by 2x. So 2 divided by 2 is just 1. You don't have to write the 1 here. And then x squared divided by x would just leave us with 1x. You subtract exponents when you divide. So x2 minus x, the 2 minus 1 would leave us with 1x. And then 10 over 2 is just 5, and then x over x would cancel. And so the factored form of this quadratic is 2x times x plus 5. So when we're factoring quadratics, our goal is to get to 2 linear factors. And so these are our 2 linear factors. One's 2x and the other is x plus 5. In this next example, we can divide each of these 3 terms by a 3. And then we can't divide them by x this time because this last term doesn't have an x. And so 3 is the best we can do as far as a GCF goes. And so 3 divided by 3 is 1 for the x squared term. Negative 12 divided by 3 is negative 4 for the x. And then 6 divided by 3 is 2. Now, ideally, we would be able to get this quadratic factor to be 2 linears, but this is actually an unfactorable quadratic, which we call prime. And you'll see how I knew it was prime in these next examples. And so these next examples, they're all trinomials, 3 terms, and the a value is 1 in each case. Those are the easiest cases to factor. You're looking for 2 numbers. I like to use the x method to organize it. You're looking for 2 numbers that multiply to 12, the c value, that add to 7. The middle, the b value. Okay, and so these numbers would be 3 and 4. 3 times 4 is 12, but 3 plus 4 is 7. So once you have those numbers, those are going to show up in your factors. So this factors to x plus 3, x plus 4, either order. In this next example, we're looking for 2 numbers that multiply to 10, but add to 7. Those numbers are 2 and 5, and so x plus 2, x plus 5. In this next example, we're looking for 2 numbers that multiply to 15, but add to negative 8. Okay, you gotta be careful with negatives, and so we're trying to multiply to 15, so 3 and 5 will work, but to add to negative, they would both have to be negative. And so our factors this time would be x minus 3, x minus 5. Whenever the c value is positive, but your b value is negative, both of these magic numbers will be negative. Okay, and then for the last example, we need 2 numbers that multiply to 21, but add to negative 4. And so those numbers are 7 and 3, but we need them to add to a negative 4. Actually, that won't work, because if one of these is negative, they're going to multiply to a negative 21. And so looking at 21, if you list all the factors of 21, it's 1 and 21, 3 and 7. There's really no way to get to a negative 4 unless we make this negative, but then it doesn't multiply to a negative 21 anymore. So once you realize there's no magic numbers that work, that's when you can tell it's prime. And so up here, I know I would need two numbers that multiply to 2 but add to negative 4. And there's only two factors of 2. And there's no way to get a negative 4. So that's how I knew that quadratic was prime. Okay? And so these next few, they're going to be special cases, but still the same method. All our a values are 1, so we just need two numbers that multiply to 16 but add to 8. In this case, they match. It's 4 and 4. So our factors would be x plus 4, x plus 4. And when they match, we can write it as x plus 4 squared. That's called a perfect square trinomial. Whenever you can write it as a perfect square, meaning the factor is repeated, it's called a perfect square trinomial. Okay, and so all of these are actually going to be perfect square trinomials. We need two numbers that multiply to 25 but add to 10. That would be 5 and 5. And so our factor, or our perfect square trinomial, would be written as x plus 5 squared. In this case, we need two numbers that multiply to 9 but add to negative 6. And so those numbers would be negative 3 and negative 3. And so we get x minus 3 squared. And then here we would get x minus 7 squared. So something you might have noticed is that this number will always be exactly half of whatever your middle number is, your b value. And it's going to have the same sign and everything. This is going to be very useful when we get to completing the square. And so just recognizing that pattern. Another special case is when our b value is 0. Okay, and so all of these, or these two, have an a value of 1, but we're going to see a pattern. Okay, so our b value is 0. And so for this first example, we need two numbers that multiply to negative 25. That's still our c value, but add to 0. And so those numbers would be 5 and negative 5. So that's not the same. So we can't write it as a single perfect square trinomial. We need them both. One's an x plus 5, one is the x minus 5, either order. And so this one's similar. We need two numbers that multiply to negative 81 but add to 0, and so that would be 9 and negative 9. But if you skip to this last one, we're looking for two numbers that multiply to positive 16 but add to 0. And so those numbers actually don't exist, because if we choose 4 and negative 4, those would multiply to negative 16. If we choose negative 4 and negative 4, or positive 4 and positive 4, they won't add to 0. So you have to have the same number here, one positive, one negative, and that won't work, and still multiply to a positive here. So anytime you have a plus sign between your two terms, and there's not an x here, it's not a GCF situation, because over here we had two terms, but it was a GCF situation because of this x. Here we don't have a GCF, and so this is just a prime quadratic. Okay, and so these are called difference of squares, keyword difference, because they have a minus sign, And anytime you're dealing with two perfect squares separated by a minus sign, there's actually a shortcut that can save us some time. You just square root the first term, square root the last term. So square root of x squared gives us the x, square root of 25 gives us the 5. And you're just going to write those terms twice, one with a plus, one with a minus. Okay, and so that saves us time for bigger a values. And so if we use that method here, the square root of 4x squared would be 2x. Square root of 1 is just 1. And then because the middle term was 0, you know you're going to have the minus and the plus. Kind of like with complex conjugates, that middle term canceled. And so the key is you have to recognize that it's minus. All right, the last few examples come up often. It's when your a value isn't 1. And so we have some added steps when your a value isn't 1. And so you still need your magic numbers, but this time you need your magic numbers to multiply to a times c. And so I need two numbers that multiply to 6 in this example, but still add to the b value. And so these numbers would be 2 and 3. But you can't skip to writing x plus 2, x plus 3. Just looking at that, you know something's wrong. Because if I multiply x times x and FOIL this back out, it's not going to get me a 2x squared. It's just x squared. And so what we do with the 2 and the 3 we just found is we split this 5x into 2x plus 3x. That's why we needed it to add to 5. And so bring down the rest of the quadratic, the first and the last, and then what we do is we split the middle and divide 2 at a time. It's called factor by grouping. So you're going to factor out a GCF from each side. And so for the left side, we can factor out a 2x. And so 2x squared divided by 2x is 1x, and then 2x divided by 2x is just 1. You have to write the 1 when that's all that's left. For the second pair, we can divide by 3, leaving x plus 1. Now, if you've done everything correctly up to this point, the parentheses should match. So that's a good way to check your work. If they don't match, you did something wrong. You either had the wrong magic numbers or the wrong GCFs. And so that x plus 1 becomes one of your factors. The other factor comes from the terms outside the parentheses, 2x plus 3, in that order. Okay, and so the factored form would be x plus 1 times 2x plus 3. And if you were to FOIL this back out, you would get your 2x squared, you would get your constant of 3. So it's always good to check and make sure it's actually going to give you the result you want. Okay, so for this next one, we need two numbers that multiply to a times c. So a times c is negative 10, and we need them to add to a 9. And so 1 and 9 will work, but not 1 and 9, 1 and 10. So we just need to make the 1 negative. Then they would multiply to negative 10, but add to 9. And so remember, you have to split the middle with those magic numbers and factor 2 at a time. So we can get an x out of the first pair, leaving a 2x minus 1 in the parentheses. And then out of the second pair, we can divide by 5, which would also lead to a 2x minus 1. So the parentheses match, so that means we've done everything right up to this point. And so 2x minus 1 is one of my factors. And then the other factor comes from this x plus 5. Okay, for this next one, we need a times c, which is 3 times negative 14. That's negative 42. And we need them to add to 1. And so 6 and 7 will work. We will make the 6 negative so that it adds to a positive 1. And it doesn't matter what order you split the term in. I could put the 7x first. Your factors will just be in a different order, but it will be the same factors. Okay, and so 2 at a time, we can get a 3x out of the first pair, which would leave x minus 2. And then out of the second pair, we can get a 7, which would lead to x minus 2 as well. So the x minus 2 matches. That's going to form one of my factors. And then the 3x plus 7 is going to form the other factor. Okay, and then for the last one, we need two numbers that multiply to negative 3, but add to the middle term 2. Okay, and so trying 1 and 3, we just need to make the 1 negative. Okay, divide down the middle. We can get an x out of the first pair, leaving a 3x minus 1. And then we can't get anything but a 1. You'll always at least be able to get a 1, which would lead to a 3x minus 1. So 3x minus 1 is one of my factors. X plus 1 is the other factor. So the factoring part's the hardest. Once you learn how to factor, you can then use that method to solve equations. So looking at this next few examples, it says now solve. That is very different than factoring. Okay, so when it says solve, there's going to be equal signs. Here we were just factoring. And so when you're factoring, you're just getting the parentheses like this. When I say solve, you're trying to find what x equals, like when you use the quadratic formula. Factoring is just the method. And so same steps. Here you need to find two numbers that multiply to 12 but add to 7. Our a value is 1, so this is going to be nice and easy. Those magic numbers are 3 and 4. And whenever your a value is 1, you can skip straight to writing those factors with the magic numbers. Okay, and so now this is set equal to 0. And so the point of having linear factors set equal to 0 is if you have a product that equals 0, that means one of your factors had to have been 0. If you multiply two things and get 0, one of those things must have been 0. And so these parentheses, these are your factors. These are not your solutions. Your solutions come from setting each factor equal to 0 and then solving. So in this case, we get x equals negative 3. In this case, we get x equals negative 4 as our solutions. Okay, and so the idea is you set the quadratic equal to 0, just like when you use the quadratic formula. You get your factors, set each factor equal to 0, and solve. And so this is our difference of squares that factors to x plus 5, x minus 5. And then when we set each factor equal to 0, we would get x equals -5 and x equals +5. Okay, here our a value isn't 1, so it's going to take a little bit longer to factor, but it's just that added step of splitting the middle and factoring 2 at a time. And so here I need two numbers that multiply to -10 but add to 9. And so those numbers will be 1 and 10, making the 1 negative. And then we split the middle with the -1 and 10. We can get x out of the first pair, leaving a 2x minus 1. We can get a 5 out of the second pair, leaving a 2x minus 1. So that means 2x minus 1 is one of the factors, x plus 5 is the other. And then it still equals 0. And so now we can set each factor individually equal to 0 and then solve. And so in this case, we would have 2x minus 1 equals 0. In this case, we would have x plus 5 equals 0. So here, subtract 5, and you have your solution x equals -5. Here we would add 1 and get 2x equals 1, and then divide by 2, x equals 1/2. Okay, let's get to number 9. So when it's not equal to 0, you have to set it equal to 0 first, just like you do with the quadratic formula. And so we would rewrite this as 12x squared minus 13x minus 4, and then factor it. So my c value is -4. Okay, and so a times c is -48. My b value is -13. And so two numbers that multiply to 48, 3 and 16, and if we make the 16 negative, this will work. Okay, and so we're going to split the middle into 3x minus 16x. And then out of the first pair, we could divide both of those by 3x, leaving us with a 4x plus 1. And then we haven't had an example like this yet, but whenever your leading term is negative, your GCF is automatically negative. It doesn't matter what this is. Okay, and so we can also divide by a 4. And so -4 is what we're dividing by, leaving us with a positive 4x, positive 1. -4 divided by -4 is positive. And so the 4x plus 1 matches. That's one of my factors. And then the other factor is 3x minus 4. Remember, it all still equals 0. And so now we set each factor equal to 0. Okay, in this case, we subtract 1 first, then divide by 4. And so x equals -1/4. And in this case, we add 4 first, then divide by 3. And so x equals +4/3 is our other solution.